What we're going to do in this video is to derive a full and complete expression for the gain of a well-designed common emitter amplifier. Now, first I'm going to do it by substituting in a small signal model for the transistor, but then in the second part of the video, I'm going to show you how you can do it all by inspection. So let's go ahead and get started. In a common emitter configuration, we are going to have a source, V sub s, and I'm going to assume that it's small in this derivation so that we don't worry about things like saturation and cutoff. I'm then going to assume that the transistor is in the forward active mode, meaning we have a nice and high voltage up here at the collector, a medium voltage at the base, and then a smaller voltage at the emitter. That's going to allow the amplifier to work correctly, just as we expect. We then have a load resistor. And what I'm interested in ultimately finding here is an expression for the load voltage, V sub L, divided by the source voltage, V sub S. In other words, I want an expression here for the gain. Let's now draw the small signal equivalent model. In other words, what circuit does a small AC signal see when it travels through this amplifier? Well, we've just reached a capacitor, and I'm now going to assume, again, that the amplifier is well designed. That capacitor actually forms a high-pass filter with the input impedance of the amplifier, but we're going to neglect it. In other words, we're just going to assume that the capacitor is large enough that the AC signal can just go right through it like a short circuit. We now have two branches. We have resistor R1 that leads to a DC source, or an AC ground equivalently, and then we have resistor R sub 2 that leads down to a real ground. We now enter our transistor, and I'm going to replace the transistor with a mathematical model. The model works like this. If current I sub B enters the base of a transistor, then the transistor acts to amplify that current by some value, beta, and send it down the collector. The transistor contains a small resistance between the emitter and the base called little r sub e. This is basically the circuit model that I'll be using here. Now, in some textbooks, they have even more complicated circuit models in order to handle things like parasitics, how the transistor behaves at high frequencies, large output impedances, but I found this to be a reasonably good model for most applications, so that's what we're going to go with here. Now, up here at the collector, the transistor is connected to a resistor R sub C that leads to an AC ground. It's also connected to a load resistor, R sub L, that leads down to a real ground. Let's label our output voltage, and then down here at the emitter, we have two resistors, R sub E and RE1. The circuit is still a little bit complicated, so I'm going to redraw it one more time. The first thing I'm going to do is to replace this slightly complicated source with a Thevenin equivalent voltage source. In order to find the Thevenin equivalent source, we need to kind of assume that nothing is connected to the circuit to the right of the green line. We find the voltage at that point, the open circuit voltage. It's just a simple voltage divider here, set up by the two resistors R1 and R2 and the source impedance R sub S. The Thevenin equivalent resistance here is obtained by zeroing out all of the sources and looking back and seeing what resistance you see. Well, if we zero out source V sub S, we dial it down to 0, then source resistor R sub S is just grounded. We therefore just have R sub S in parallel with R1 in parallel with R2. Let's now redraw our circuit. There's our Thevenin equivalent voltage source, and there's our Thevenin equivalent resistance. For the rest of the circuit, we can simplify things a little bit by combining R sub C and R sub L, and then we can combine three resistors at the emitter side as well. In order to make some headway here with solving this circuit, I'm going to apply the Kirchhoff voltage law around this loop. The voltages should sum to 0. First, we have a voltage rise of VTH. Then we have a voltage fall given by the base current times the Thevenin resistance. And then we have a voltage fall across these resistors over here. The current through those resistors is beta plus 1 times IB. And those all have to sum to 0. I now see that I sub B appears twice in this expression, so I'm going to factor it out, and I'm going to move the negative terms to the right side of the equation. Let's now solve this expression for I sub B. Let's now apply Ohm's law across these resistors up here. R sub C in parallel with R sub L. V equals IR, so we have the load voltage, we have beta IB, and it's negative because it's going up rather than down here. And then we have the resistors. I already have an expression over here for I sub B, so I'm going to now substitute that in to my expression for the load voltage. Let's write it over here to the right. So we have the Thevenin equivalent voltage and then everything in this denominator. Let's now rewrite this expression, but I'm going to make some substitutions along the way. So first I'm going to write my expression for the Thevenin equivalent voltage source, and we have that over here. For this Vs, I'm going to move it over here into the denominator so that it's in the right position to find the overall voltage gain. We now have everything else in this expression to write, and when I rewrite it, I'm going to divide every term by beta plus 1. Therefore, in the numerator, we're going to have beta divided by beta plus 1. And then in the denominator, we're going to have the Thevenin equivalent resistance divided by beta plus 1. And then I can get rid of it here for the last expression. Beta is going to be very nearly equal to beta plus 1, because if beta is 100 and beta plus 1 is 101, then these are within 1% of each other. Let's just simplify this and say that they're nearly equal to 1. Beta plus 1 is also very nearly equal to beta. Let's rewrite the expression for the gain, and we're very nearly at an answer. So we have one expression due to the Thevenin equivalent voltage source, and then we have another due to the gain and the output side of the circuit. Let's substitute in for our RTH down here. It's just R1 in parallel with R2 in parallel with R sub S, and I'll divide it by beta, and then we have over here our emitter resistances. If we look at our expression, we see that we have two terms here. We have basically an input voltage divider. We have a negative sign. This is an inverting amplifier, isn't it? And then we have some resistances, and if we kind of look at all of them, we see that in the numerator, we have an effective resistance at the collector. You see, connected up here to the collector are RC and RL. Then down here at the bottom, we have a bunch of resistances connected to the emitter. We have these two resistors in parallel. Those are in series with the emitter resistance, and then those are in series with a bunch of resistance reflected over from the base. Let's now go ahead and find the same expression for the voltage gain using impedance reflection and inspection. You're going to find that it's a lot easier, but we'll wind up ultimately with exactly the same expression. Let's go ahead and get started. You're going to like this method a lot better because everything is easier. So we're going to look at two different options. Option 1 will be to reflect the base into the emitter. In other words, we're going to take all of the resistors on the base side and divide them by beta in order to move them over to the emitter side. Option 2 is going to be to reflect all of the resistors at the emitter over onto the base side. You should only use impedance reflection once when you're finding expressions for voltage gain to avoid double counting things. we're going to take all of the resistances to the right of this line, including little r sub e, and we're going to move them over to the base side, multiplying by beta along the way. Let's now draw our small signal equivalent circuit for option 1. We have our source voltage, our source impedance, and then we have a voltage divider, R1 in parallel with R2. We're going to stop right here, and I'm not going to use impedance reflection to bring anything onto the base side because we're going to be using that on the emitter side instead. We now have our gain section, and the gain of a common emitter amplifier is given by resistance at the collector divided by the resistance at the emitter. So our resistance at the collector is R sub C. Down here in the denominator, I now need to include all of the resistors attached to the emitter of the transistor, and I'm going to be using impedance reflection to bring over all those resistances from the base as well. Starting with the resistors attached to the base, we have R1 in parallel with R2 in parallel with R sub S, and I'm going to have to divide everything by beta. What else do we have attached to the emitter? Well, we have little resistor R sub E, and that's in series with these two resistors R sub E in parallel with RE1. The output impedance, looking back into this circuit, is just R sub C because looking down into that collector is something like a current source, so it has a very high output impedance. And then finally we have our load resistor. This is a simple enough circuit that we can find an expression for the gain by inspection. First we have a voltage divider set up by these resistors. I could call this the input side. Then we have the gain section that's given by whatever we have written next to this source. It's important now to point out that I shouldn't label this V sub B because it's not a true expression for the base voltage. If I wanted a true expression here, then I should use impedance reflection on the right side. I'll label it V sub 1 in order to take care of that technicality. Our gain section here is going to be whatever I have written next to this source. And then now I have an output voltage divider given by our load resistor and our output impedance. We can then label these accordingly. By the way, if you look at part of the center expression and then the entire output section, you might notice that this just equals RC in parallel with R sub L. So you can also think of the gain section as just being all of the resistors attached to the collector divided by all of the resistors attached to the emitter. And if you think of it that way, then don't include the output section. Let's now move on to option 2 and draw the small signal model. We again have our source, our input impedance, and we're going to neglect the capacitance by assuming that it's large enough that the small signal should just go right through it. We then have R1 in parallel with R2, and then we have a third branch that goes into the base of the transistor, and we'll be using impedance reflection in order to find it. It's going to be R sub E plus these two resistors in parallel. And of course, this all has to be multiplied times beta since we're using impedance reflection. We now have our gain section. Our gain is going to be what's connected to the collector of the transistor and divide it by whatever's connected to the emitter. So there's the collector part. Now for the emitter part, we don't want to use impedance reflection, so I'm only going to be including little r sub E and the two emitter resistors in parallel.
We used impedance reflection on the left, so we don't want to use it again on the right.
We can then go ahead and draw the output section of the circuit. Let's label everything accordingly. We're going to have an input voltage divider, we're going to have a gain section, and then we're going to have an output voltage divider. We can write our expression for the gain by inspection. We have first a voltage divider at the input side, and what I should really do is to go back and label this voltage, and here I'm actually going to label it V sub B because it's a true expression of the AC base voltage here. And it's true because I've used impedance reflection in order to find it here on the input side. We now have our gain section, which is basically just the resistors attached to the collector divided by the resistors attached to the emitter. And then we have another voltage divider set up by the output impedance of the circuit. We now have two different expressions for the overall voltage gain. It turns out that these two expressions are identically equal to one another, and it's not obvious that that's the case. It's not even easy to prove that these are identical to one another. So what I've done is I've keyed both of these expressions into Mathematica, a computer algebra program, and I've let it do all of the hard work for us. You can see here that I've defined gain 1 from option 1, and I've defined another variable, gain 2, from option 2. And then we've asked Mathematica whether these two are equal to one another, and it says that they are. I'm sure that if you had a lot of time to spend, you could do this by hand and find that they're equivalent to one another as well. But I'm going to take the software's word for it. Let's now find expressions for both input and output impedance for the common emitter configuration. Looking into this amplifier, we pretty much see two resistors, R1, which leads to an AC ground or a DC power supply, and R2, which leads to ground. We then have a third branch that goes into the base of that transistor, and I'm going to have to use impedance reflection in order to find out what that impedance is. In order to bring all of the resistors on the emitter side over to the base side, I need to multiply times beta plus 1. We therefore here have beta plus 1 times the emitter resistance R sub E, which is in series with the other two resistors down here at the emitter. By the way, sometimes the resistor looking into the base of a transistor is called R sub pi. It's from something that you'll see in some textbooks called the hybrid pi model. It all boils down to how you want to describe this transistor's behavior mathematically. If you have a collector, a base, and emitter, one way to model a transistor is to do what I've been doing, and that is to say that it's a current source that multiplies the base current times beta and sends it down through an emitter resistor, little r sub e. What the hybrid pi model does is something very similar, except that it includes the resistance that I've put on the emitter side on the base side. It's then called r sub pi. The two models are entirely equivalent to one another. Using impedance reflection, you can even say that r pi is just beta plus 1 times r sub e, and you could redo all of the derivations that we've already done. I think that it's pretty much the same, but the reason why I like using r sub e instead of r sub pi is simply because when you look at the transistor, there's a big line right here that separates the base from the emitter, and there's space here to draw a little resistor and remember where it is. Let's now move on to the output impedance. Now, the output impedance of the common emitter configuration is exceptionally easy to find because if you look back, you see one resistor, R sub C, that's connected to an AC ground, and that's in parallel with some resistance looking down into the transistor. In some models, that resistance is labeled R sub O, O standing for output. But this is typically a really big number because you're looking down into something that's similar to a very good current source. So this is typically neglected as being large. So we can just approximate the output impedance here as being R sub C. R sub C, by the way, affects the gain of the transistor circuit. So here we're left with a bit of a conundrum. On the one hand, we want a little r sub c in order to give us a desirably small output impedance, but we, on the other hand, want r sub c to be large so that our gain is high. Therefore, it's impossible to have both of these things true at the same time with only a common emitter configuration. Let's now work a couple of example problems and find accurate expressions for the voltage gain, input impedance, and output impedance for some common emitter amplifiers. So in example 1 here, we're looking at a reasonably well-designed common emitter amplifier, and we're tasked with finding the input impedance, the output impedance, and the overall voltage gain. Now, usually when you're looking at a well-designed amplifier, you can estimate the voltage gain by inspection. So let's go ahead and do that before we start doing any complicated calculations. When I look at the input side of this amplifier, I can ask myself, is the source impedance small relative to the input impedance of the amplifier? The input impedance here of the amplifier is going to be on the order of kiloohms, and the source impedance is only 100 ohms. So I guess we're not going to have too much attenuation at the source side. Now, how about for the gain? Well, the gain of a common emitter configuration is just R sub C divided by R sub E. So 1 kilo ohm in parallel with 500 ohms is going to be something like 300 ohms. 700 divided by 300, okay, we're going to have a gain of about 2. On the output side, however, I see that my load resistor is 700, and that's very similar to what the output impedance of my circuit is. So I'm going to again have an attenuation at the output side, and the attenuation is going to be by a factor of 2 or so. So with a gain of 2 and an attenuation of 1/2 at the output side, I predict that the overall voltage gain for this amplifier is going to be just about 1, or -1, if you remember that it should be an inverting amplifier. Let's go ahead and do a more robust or more rigorous calculation here to find out what the gain actually is. First of all, let's find the input impedance. We're going to have a branch of 10 kiloohms, a branch of 8 kiloohms going to an AC ground, and then we're going to have a third branch going into the base of the transistor. We'll use impedance reflection in order to find it. Therefore, it's going to be beta plus 1 times these resistors down here at the emitter. Let's find the DC characteristics of this transistor amplifier so that I can find out what R sub E is. Well, my base voltage, V sub B, is going to be the power supply voltage times a resistance divider set up by these two resistors. That works out to be 4.44 volts. The voltage at the emitter should be around 0.7 volts below the base voltage. That's 3.74 volts here. This allows me to find my emitter current, I sub E, which is all going to flow through the 1 kilo ohm resistor. None of it's going to go through this branch here on the right because the 100 nanofarad capacitor will block it. We're doing a DC analysis, remember? With an emitter current of 3.74 milliamps, I now have everything I need in order to find the emitter resistance, R sub E. It's just going to be 26 divided by that emitter resistance expressed in milliamps. It works out to be 7 ohms here. I can then substitute in an estimated beta of 100 and an emitter resistance of 7 ohms in order to find an accurate expression for the input impedance. Everything in green here works out to about 34.4 kiloohms. It's a reasonably large number relative to the other two resistors, so it wasn't strictly necessary here in order to find the input impedance. It winds up being 3.9 kiloohms. I'll write the words good and high here because that's a good and high input impedance when we compare it to our 100 ohm source resistance here. Let's make a note and just say that if I had not used impedance reflection and I had only considered these two resistors looking into the input side of the transistor amplifier, I would have gotten a number of 4.4 kiloohms for the input impedance. That's still a reasonably good approximation, and it's not going to affect our gain calculation too much in either case. The output impedance to the circuit is just 700 ohms because we're going to neglect the resistance looking down into the collector. Let's now find an expression for the overall voltage gain. We're going to have an input section, a gain section, and an output section. We're going to first have a voltage divider set up by the source resistance of 100 ohms and the input impedance R sub N. I'm going to make a note here to remind myself that I used impedance reflection already in order to find R sub N. We now have our gain section, and the gain of a common emitter amplifier is just the collector resistance divided by the emitter resistance. When I find the emitter resistance here, I'm not going to use impedance reflection because I already used it on the input section. Therefore, we have the resistance at the collector, and then for the emitter, we're going to stop at RE. We now have a voltage divider at the output side set up by our load resistance and R sub C. If we plug in numbers for all of these terms, our input divider gives us 0.975. Again, the circuit has a nice high input impedance. Our gain here is negative 2.06, and then our output divider gives us a gain or attenuation here of a half. Our overall gain is negative 1, just like we estimated through inspection. Example 2 here is just a little bit trickier because you can see that at the emitter side we have only a large capacitor. We've completely bypassed the 1 kilo ohm resistor here for AC signals. Let's first do a DC characterization of this amplifier. We have a 10 volt power supply and two 10 kilo ohm resistors. Therefore, our base voltage should be halfway between 10 and 0, or 5 volts. Our emitter resistance should be down by 0.7 volts, assuming that it's a silicon transistor. That gives us 4.3 volts at the emitter. All of the DC current is going to go through the 1 kilo ohm emitter resistor. Since it's 1 kilo ohms, we have 4.3 milliamps flowing through that resistor. I have enough information now to determine my emitter resistance, little r sub e, that sits between the base and the emitter. It's just going to be 26 divided by 4.3 here, 6 ohms. It's also worth remembering at this point that 26 is Boltzmann's constant times the temperature. So this 26 is what that works out to at room temperature. If you heat up the transistor runs hot, then the temperature is going to go up and the emitter resistance is going to go up. Whether or not that causes the gain to go down or up depends on the kind of circuit that you're dealing with. Let's go ahead and find the input impedance R sub N. We have 3 branches. We have 10 kilo ohms going to an AC ground. We have another 10 kilo ohms going to another AC ground. And then we have a branch going into the base of the transistor. And I'll be using impedance reflection in order to find it. We'll have beta plus 1 times the emitter resistor R sub E, but we have 0 resistance in parallel with 1 kilo ohm. So 0 in parallel with 1 kilo ohms is just 0. If we plug in 100 here for beta and 6 for R sub E, we can see that bypassing the emitter resistor has lowered our input impedance substantially compared to the last example anyway. The two 10 kilo ohms in parallel with one another give us 5 kilo ohms, but the impedance from the emitter side lowers it down here to 606, and when we calculate everything out, it's 540 ohms. That's a kind of low input impedance, so you can see what's happened here is that by bypassing the emitter resistor with that 100 nanofarad capacitor, we've effectively loaded down our base. We've made the input impedance worse. If we look at this circuit and we estimate the input impedance as being 5 kilo ohms, by looking at these 2 resistors here at the input side, we're going to get a bad estimate. So anytime you see this kind of capacitor at the emitter side that's bypassing some resistors, ask yourself, am I lowering down my input impedance? That's exactly what's happened here. The output impedance to this circuit is just 1 kilo ohm. We can neglect the output impedance looking down into the collector. Let's now find the overall gain. We're going to have an input section that's given by a voltage divider set up by the source impedance of 100 ohms and our input impedance. I'm going to make a quick note to myself that impedance reflection was already used here. We then have a gain section, and the gain of a common emitter amplifier is the resistance attached to the collector divided by the resistance attached to the emitter. So here we have negative 1 kilo ohm. That's the collector side. And then at the emitter side, we have only the R sub E because we have a short circuit here in parallel with 1 kilo ohm. I did not use impedance reflection to bring in the resistors from the base. The reason I didn't use it here is because I used it over here at the input side, and you only want to use it once when you're dealing with the common collector or the common emitter configurations. Let's write 0 in there just to make it clear. We then have our output side. It's our load resistance in a voltage divider with our collector resistance. When we plug in all of the numbers, we find out that our input side gives us an attenuation, 0.84. Our gain section gives us a very large gain of negative 167 here, and then our output side gives us 0.33 here. Our output impedance is kind of large relative to our load. When we multiply all these numbers together, we find a gain of negative 46. That's a nice high gain, but there's a bit of a caveat here that I should point out. The gain is sensitive to R sub E, and R sub E is sensitive to the temperature. This means that if you actually build the circuit and you heat it up or you cool it down, then the gain is going to deviate a bit from what you might expect through this simple calculation. In the last video, we looked at the common collector configuration in detail, and in this video, we've just wrapped it up for the common emitter configuration. So we're left with just one configuration for the bipolar junction transistor, and that's the common base. In the next video, we're going to do the same thing with the common base amplifier. We'll find detailed expressions for the gain, and then we'll work some practical examples.